Hi everyone, welcome to another video. Now, this is just a bit of a random one-off proof video in which we're going to marry two ideas which we've talked about previously on this channel. This is Pythagoras' theorem, which we've talked about at length, and similar triangles. Now, what we're going to do is we are going to prove Pythagoras' theorem using things we know about similar triangles. So what I'm going to do here is I am going to just give you this big triangle here. Now, Pythagoras' theorem tells us that this length A, this length B, this length C. Pythagoras' theorem tells us that length A squared plus the length B squared equals to the length C squared. Now, in the context of these particular markings we have in this question, I have the line AB, I have the line BC, and I have the line AC. So my Pythagoras' theorem here is going to look like the line AB squared plus the line BC squared is going to equal the length of AC squared. So this guy over here is what we are going to try to get to by the end of this video. Now, similar triangles are a really useful way for proving Pythagoras' theorem when we don't actually have any values associated with these sides. Now, before, we looked at a couple of different methods for proving Pythagoras' theorem. We looked at Pythagorean triads and things like that. But now we are looking at purely a triangle with no actual markings. Now, the first thing we're going to do is we are going to, because you're thinking probably, how are we going to use similar triangles if we only have one triangle? Well, what we're going to do is we are going to draw a line from this corner B over to this hypotenuse AC. And we're going to draw it so that this line makes a 90-degree angle with the line AC. And we're going to call this D. So I have a new line, BD, which is perpendicular to the line AC. And now this gives me three right angle triangles in total. I've created two new right angle triangles. So I've created this little one here. I've created this medium-sized one here. And I have my original big right angle triangle out here. So we are going to dissect and break up all of these three triangles. And before we can even think about Pythagoras' theorem, I want to prove that all of these triangles are similar to one another. So let's get started on that. Now, let's first consider the the medium triangle here and the big triangle here. Okay. So first of all, we are going to introduce these two triangles. So we are going to write out our similarity statement. So in triangle ABC and triangle BDC. So we are looking at my big triangle and my medium-sized one. Now we can say in both of these, we're given in the question that we have a 90-degree angle. So in both of those, we have one equal angle of 90 degrees, and that is given to us in the question. Now, looking at these two triangles, they actually share a common angle at the vertex C. Because this angle, it belongs to both my big triangle The angle C still lives inside it, as well as my little triangle. This angle C lives inside that one too. So we can say here as well that angle C is common. And we have two angles now, which means that the third one must also be equal. If we have two equal angles, the third one's going to be equal because all angle values in a triangle, the three angles, add up to 180. So angle for similarity is enough to tell me that two triangles are similar. So I'm going to say, therefore, triangle ABC is similar to triangle BDC. Okay, sweet. And I'm just going to draw those for good measure as well. So I have triangle A, B, C, and I have triangle BDC. These two are similar. Now I can do the exact same thing with the remaining two combinations. Let's compare triangle, my big triangle ABC, to triangle ADB. So this smaller one up here. So let's introduce those two. In triangle ABC and ADB, we're going to make another couple of observations. Now, the first little part of this video is us just proving the similarity. If you want to get through to the rest of the proof when we introduce Pythagoras' theorem, feel free to skip ahead. But I'm just doing this nice and slowly so we can really break down what's happening here. So in my big triangle ABC and my smallest triangle ADB, let's make a couple of observations. Now, once again, they have two 90-degree angles in them. So they have one equal angle that's given in the question. And also they share a common angle of A. Because once again, noting that this angle A belongs to my big triangle ABC as well as my little triangle ADB. So once again, we have two angles that are the same. So these two triangles we can say are similar. Now, because we've pretty much used the same information, I'm just going to do these quotation marks because they have a common 90-degree angle and angle A is common. So therefore we can say that triangle ABC is similar to ADB by angle. And I forgot to write that here, so let's write that in. So angle we've used 2 times to prove similarity. We're going to do it one more time. Actually, let's draw these in first. My big triangle ABC, that is similar to triangle, let's draw a really small one here, ADB. And finally, we're going to look at another 2. So we're going to look at this time my smallest triangle, ADB, as well as my triangle here. BDC. Okay, so for this one, we have already proved something very important with the similarity of the other 2. Because here it may not be immediately obvious that these are the same, but in order to answer this, we are just going to use a little bit of some observations we made from the previous proofs. Now, these two triangles, because they're similar, we have that this one is the same as this one, and this one is the same. Oh, sorry, these two are the same, I should say, and these two angles are the same. That's what we proved in the previous couple of proofs. And also, we have, once again, the vertex of A. Here, these two are the same. They're common. And B and C are also common. Well, they're going to be equal. We've already proved this. We've done the heavy lifting already. So if we just draw in my triangles A, D, B and B, D, C, if I draw those in, so my medium-sized one here, B, D, C, that one is exactly the same because we have a link here. We have linked the big one, biggest triangle, with the smaller one, and we've said that those are similar. Now, if my big triangle is similar to my medium-sized triangle, and my big triangle is similar to my small triangle, all of these are similar. Therefore, using that logic, we can say that these two are similar. The missing link between these is the fact that the biggest triangle, ABC, is similar to both of those. So therefore, we can say, because of that, that the medium one and the small one are similar. These are similar triangles. Okay, now we're going to make one more observation before we go into the actual proof of Pythagoras' theorem. Now, because these are similar, we're going to note a couple of things. Now, remember, when we have similar triangles, that means that the sides, all the sides are in proportion. So they have the same scale factor. So you divide one by the other, you're going to get the same number. Now, these are similar, which means that the side AB, which I've highlighted in orange, the ratio of that to BD is going to be equal to the ratio of BC, this blue line, to DC. So BC to DC, these are the two blue ones, and those ratios, those ratios are going to be equal to my green highlighted lines. So AC over BC. So this is just what we already know about similarity. When we have similar triangles, the proportion or the scale factor of each side, each corresponding side, is the same. And I've just written that down here. Now, same thing with this one. My side AB over AD, that will have the same scale factor as BC to DB, which then in turn has the same scale factor as AC to AB. So let's write that in as well. So we have that AB over AD is equal to AC over AB, and that is also going to be equal to BC over DB. Okay, so this is just us stating a few things we know, because we're going to need all the help we can get in order to prove Pythagoras' theorem using this. So once we've proved similarity, I'm trying to make as many observations as I can based on what we know. So finally, for these, I can also say, well, okay, the ratio of BD to AD is the same as the ratio of BC to AB, which is the same as the ratio of DC to DB. So finally, I'm going to write my last piece of information here, which is going to help us to solve this question. So we have CD over BD, and that's going to be equal to CB over AB. Okay, so for the actual proof, because remember the thing we are trying to prove here is that AB squared plus BC squared equals to AC all squared. And we have a couple of these written out in our notes. So I'm going to isolate a couple of parts of these little statements here, these equal statements about the sides. So what I'm going to do is I'm going to use this guy here because this shows me AB, and I'm going to show, I'm going to get this one here as well. Oh, actually, we want BC, so I'm going to get the one with BC's here. Okay, so this one also has a BC in it as well. Okay, so let's start our actual proof properly. So I've identified that all of these are similar triangles, and I've made a link between the ratios of the sides. So let's just write down everything we know so we can move on to our actual proof. Okay, now for this proof, we noted that BC over DC equals to AC over BC, and we also said that AB over AD is equal to AC over AB. These are the two things we stated. Now, if we look here, I have a BC on either side of this equation. I also have an AB on either side of the equation. So what I'm going to do is I'm going to rearrange through cross multiplying here. So let's rearrange this. So what I'm going to do is I'm going to multiply both sides by BC to get these together, as well as both sides by DC. So cross multiplying this gives me on the left hand side BC times BC equals to AC times DC. So all I've done first is just multiply both sides by BC. That cancels this. And I've also multiplied both sides by DC. That cancels this. So that's why we get the AC and the DC together on one side and the two BCs together on one side. Now, when two BCs, two lengths, so some number, when the same number multiplies by itself, we can say that that number is squared. So we can say that BC squared equals to AC times DC. And doing the same thing here, doing the same cross multiplication, I get AB times AB on the left hand side, because here multiplying both sides by AB is going to cancel the denominator from the right-hand side. And on the right-hand side of this equation, I'm going to get AC times AD. Okay. Now, it's a lot of steps, I know, but we're in the home stretch now. So also, I have two ABs multiplying by each other. This gives me AB all squared. And on the right-hand side, I get AC times AD. Okay, now Pythagoras' theorem states that one side squared plus another side squared equals the third side all squared. So if I draw out my original triangle, here I have A, B, C, and I have this one D as well. We're trying to show that AB squared plus BC squared equals to AC squared. Now let's just make a quick observation about AC, about the length of AC. I make the length AC up from adding the length AD and the line DC. So I'm just going to write that down because that's going to be important here. So I'm going to say that the line AC is made up of AD and DC. Okay, so I have these two here and here. Now I want to just add those together. I want to add these two equations together because for Pythagoras' theorem, we're going to be adding the two lengths together to see what to see if that equals to the hypotenuse squared. So what I'm going to do, let's call this equation 1 and equation 2. I'm going to add both of these together. So what I get is on the left hand side, I'm going to add my AB squared plus my BC squared. And on the right hand side, I'm going to add my two values here. So I get on the right hand side AD times AC plus AC times DC. Okay, now this is where we do a little bit of mathematical manipulation. I have half of my Pythagoras' theorem, but we somehow want to make AC squared out of everything on the right-hand side. How are we going to do that? Well, first of all, we're going to notice that both of these terms have a common factor of AC. So I'm going to pull that out. So my AB squared plus BC squared equals to, I'm going to pull out AC, and I'm factorizing these two. So I'm going to get AD here plus DC. But let's look at what we identified up here. My AC is made up of AD plus DC. And I have AD plus DC here. So instead of writing AD plus DC, I'm going to replace that with AC. So I have AC here, the one out the front, and that's multiplying by AC again, because AD plus DC equals AC. Okay, we're almost done. When I multiply two things that are the same, I can square those. And hence I'm left with AB squared plus BC squared equals 2AC squared. I have proved Pythagoras' theorem using similar triangles, in that one side squared, AB squared, plus BC squared equals 2AC squared. And I have that there. Now, I know that was a long video. If you have made it to the end, thank you so much for watching. And it's a very long process, and it's a hard process. This isn't something that we can just do in like 2 minutes and figure out. It takes a lot of hard work, and it takes a lot of understanding conceptual ideas about similar triangles. So in setting up all of our similar triangles, we made notes that of, first of all, proving their similarity, and then also these ideas that the ratio of the corresponding sides are going to be equal. So we were able to set up all of these fractions here in order to make equations and eventually get to our proof. But this is how we can prove Pythagoras' theorem using similar triangles. Thank you so much for joining me, and I'll see you next time.